Okay, here in part 3 of this Waddell leg truss example, we're going to look at the average bearing stress of the pin on the I-bar of the member. Now, bearing stress you could think of as a little bit like contact stress, your foot on the ground type of thing, or take this mouse and it's resting on the tabletop. It's got a contact patch there, and in this case we've got 4 little surfaces that the mouse is actually resting on, right? Really old school, it's a mouse as opposed to just a finger pad. Right? And so you could take the weight of this mouse and divide it by those contact patch areas, and you'd have an average bearing stress or contact stress of the mouse on the table surface. We're going to do something a little bit similar, although it's slightly more complex for this pin, the same pin that we were looking at before that was connecting the vertical CG to this joint down here at C. Right? And so let's take a look at that. The member, just one of the I-bars, is transferring 100 kips through the connection. It has 100 kips out in the main gross part. The pin then has to be able to resist and be able to deal with those 100 kips. Now the pin itself then is, you get this right, my fingertips are this red arrow pointing towards that red arrow, and as we tug on those fingers, here's your shaft, and it's pushing back against the part. That's what we've got showing right here, that 100 kips that's bearing. Ultimately, in reality, whatever that contact area is on that curved surface. But that's a really complicated thing to try to understand. This bolt will actually deform and change the contact area there. And so what we do is something far more simplified as a gross model to try to have a basic understanding of what's going on. It's not going to be exactly right, but in engineering we don't always try to be exactly right. We try to be good enough, and that's what we've done over time, is to try to be good enough with these things. So we're going to find the average bearing stress. That's a normal stress. So sigma average, and we'll use the B for bearing. And since that could be confused with bending, we'll do BRG, so for average bending. So that means we need a bearing force divided by some sort of bearing area. I don't know why I wrote out bear the animal there. That was a little funny. But that's your basic model. So now we got to figure out what are the numbers and why are those the numbers? All right, so the bearing force is easy. That's the 100 kips that came from the member and the component that's being pushed through here, or pulled, that is. And then we need this area. So what we do is really a projected area. When we look at this cutting through this little piece of the I-bar, then, and remember the bolt or the pin is in this middle part, right, pushing against that inner surface, right? And so we've got this 100 kips that will effectively get split 50-50 on either side. But then we're going to just take that total of 100 and smear it out over this little projected area. This little dimension, the 1.5, that's the thickness that goes here. And so the loaded area that we're looking at is this gray shaded area. Okay, over here in the white area, that's the tensile stresses here that are coming out at you. These are the ones, that's the sigma bearing of the pin on the part that we're interested in. So that area is simply 3 inches by 1.5 inches. Now if this is really confusing to you, and it usually is for most folks the first time they encounter it, you'll get another chance at that when you take the steel course. It is a little on the sophisticated side of things, and it's also confusing to people because they're like, well, but that's not the real contact area. You're right, it's not. It's a projected area that we're really looking at here, and so we end up with then an average stress of 22.2 kips per square inch. And note the units. It's a stress quantity. It's a normal to this gray shaded area. It's an average. And really, a bearing stress is by default a compressive stress, so you don't really need to write that down too. But there you go. There's your answer.